Hello everyone, welcome back to the latest lecture session. Again we are still looking at filtration, and I believe in this session we will wrap up filtration. Filtration, we are trying to remove suspended particles but of relatively smaller sizes than those that will be removed during sedimentation, right. Let us look at what we have understood from the previous session. We know that, I guess, dual media filters, we looked at the relevant graph for this. Dual media filters in general, I guess, do better than single media filters. We looked at the relevant profile, if you remember, and without chemistry or not chemistry, coagulant or chemical treatment, this was the profile, let us say, right. This was the case when alpha was equal to 0.1 without chemical treatment or without coagulant addition upstream, let us see. And until this, I think it was anthracite, and here it was sand. And with chemical treatment, we saw that the efficiency was something like this. Again, dual media better than single, and in general for rapid filtration, you want to add coagulant, right. This was the case with alpha was equal to 1, let us say, or when we had chemical treatment upstream. And also from the relevant graphs, I think we saw that the removal efficiency will be relatively less and the particle size is 1 micron. Removal efficiency is lowest when the particle size is around 1 micron. And with respect to attachment efficiency, right, we looked at different aspects, one due to inertia, one due to gravity, and one due to diffusion, let us say, right. And we looked at how it is dependent upon the diameter of the particle, and that these two factors obviously are the principal mechanism for removal for bigger particles, and I think for the smaller not equal to, this is proportional, right. And with respect to diffusion, it is obviously for the smaller particles. This is something that we looked at, and obviously we saw that head loss will increase over time of operation, and for head loss, depending on whether it was laminar or let us say Frockheimer's flow, Reynolds number being between 1 to 100, right. We have different equations, and also within that we have equations for spherical particles and for non-spherical particles and such, and for that to take into account we also have the shape factor and such, let us see. So, I believe these were the aspects we looked at in the last session, and we were about to look at the design aspects with respect to the head loss, right. So, we looked at this aspect, yes, and we have the total head here under drain, and here obviously we have the surface arms, yes, when you want additional level of mixing during backwash. So, fluidized bed and expanded bed, well, this should not be a figure that I should use because of what I am going to discuss later, or in considering what I am going to discuss later, but in general you understand what is happening, at least within this same volume, okay, within this same volume. Obviously, relatively lesser particles will be present. Why? Now, the total volume has increased or the total height has increased, but one aspect to keep in mind is that the volume of the solid or the media particles within this depth and or within this volume and within the total volume are still the same, right. The porosity of the bed is increasing here, right. Porosity of bed is relatively less here, as you can see. Porosity of this expanded bed is now higher, but the volume of the solids itself, total volume of solids over the entire bed here and over the bed here is still the same, right. We will look at why that is relevant, and we also looked at the backwash velocity. If the backwash velocity is higher than the settling velocity of the particle, then this particle will be, or the media, here I am talking about the media will be removed. So, I do not want this to happen, that has to be kept into account, let us say, or taken into account. So, backwash velocity must be high enough to give good expansion. So, again I guess 10 to 25 depending on which particular or how dirty is the water coming in, right. You can even have higher bed expansion or such, let us see, right. So, design parameters, typical velocity is 35 to 60 meters per hour, yes, you can get an understanding of what we are talking about. And if you remember, we also looked at relatively lower what do we say filtration rates earlier, let us see, right. So, bed expansion again 30% or so. In general, thumb rule, the value of the freeboard let us say in centimeters should be greater than the value of the backwash rate. Again, that is something to keep in mind, let us say. Yes. So, between backwash and bed expansion, obviously there is going to be a relationship which we are going to use later. Let us look at what it is. Again, this is what I was trying to say earlier, the total volume of the solids does not change, right. Now, the total volume of the bed has increased, but the volume of the solids within this total bed is still the same. That is something to keep in mind. So, volume of the solids before expansion is equal to the volume of solids after expansion, total volume anyway. So, if there is a constant what do we say bed porosity, assuming that there is a constant expanded bed porosity, right, which is not always the case, but for purpose of understanding. So, this is 1 minus porosity, let us say porosity of the non-expanded bed, porosity of the expanded bed, let us say, right, and surface area, and this is the depth before expansion, and this is the depth of the expanded bed during backwash, right. So, that is what it will be equal to. This will give me an idea about the volume of the relevant solid particles or the media, let us say. Yes. So, if I play around, I can get this depth of the expanded bed. Yes. If it is not only one layer, but there are different layers with different porosities, then the weighted average with respect to the porosities and the fractions will have to be taken into account, right. So, if it is not only one bed and there are different beds with respect to, or if the expanded bed, pardon me, is stratified, then obviously the relevant weighted, this is the weight and this is the averages that we have to take, let us see, right. So, let us move on. F is the mass fraction in the ith layer, depth of the expanded bed, porosity of the bed, right, and this is porosity of the expanded bed, depth of the unexpanded bed, right, mass fraction of filter media with expanded porosity, right. Again, different aspects that you can consider, but in general for our understanding this is good enough. Surface area, obviously plan view or top view. So, what is the equation that we will use to be able to look at the backwash velocity and try to relate it to our expanded bed porosity. So, it is the Richardson-Zucchi equation, and here again it is depend upon the particle Reynolds number for the ith layer, right, and it is also depend upon the settling velocity of the relevant particles, let us say. So, that is what we have here, settling velocity of the particles here, and this I guess is backwash velocity, and this is the settling velocity as we just have that here. And typically people, at least in India, I think my TA tells me that they have asked questions based on this particular aspect in some of the exams, let us see, right. And this I guess is the kinematic viscosity, and this is the diameter or the geometric mean base diameter of the relevant particle, right. So, that is something to keep in mind. So, head loss calculation, I think we have a numeric coming up. Okay, before that we are going to look at analyzing the system. So, I am going to look at weight of the media per volume of the media, let us see, right, and that is going to give me this particular equation, I guess. Okay, so I should not have heard equal to here. So, where is this coming from? We know that now or earlier when we are looking at sedimentation, we saw that there was gravity, there is buoyancy, and then due to frictional force there is drag, right. This was during sedimentation. Yes, this is gravity and drag and buoyancy. Even now it is going to be the same, gravity is always going to be there and buoyancy too, I guess. But here the particle is not moving down, or at least the drag is due to the water moving past it, let us say, right. So, again from that you can get the relevant equation again. Yes. So, that is where you will get this equation from. That is why we have F subscript g is the gravitational force on all particles, which is equal to the drag force on all particles. That is the assumption here, let us see, right. So, force per area is related to the head loss. Yes. So, from this equation, if I take the dE out to the left hand side, depth of the expanded bed, so I will have this force per area, and that can be related to the head loss, let us say, right. And from that I am getting the equation for head loss. Yes. So, from that I am getting the equation for the head loss during that particular backwash. And here obviously I have the porosity of the expanded bed, but I know how to place that with the porosity of the bed in general. So, we have this equation, yes, and I know that this particular set can be replaced by this, This is during expanded bed when I am looking at backwash. This is the usual case, let us say, when filtration is taking place, and this is relatively easier to measure than when compared to this. So, though we have some assumptions here and such, as you can see, more or less I am concerned with this particular set of variables which I can measure easily. So, now I can get the head loss here, let us say, right, head loss during what do we say, head loss during expansion, let us say. Expanded bed head loss in terms of the unexpanded bed head loss. Note that the head loss is independent of the backwash velocity. So, one other aspect seems to be that, as can be seen here, it is independent of the backwash velocity, density of the particles and the relevant water, porosity and the depth of the bed, right. So, these are the relevant aspects, but not the backwash velocity. So, let us look at a question or a numerical here to better understand the relevant aspects and the applications. We have a sand filter and we are trying to cater to a 2 lakh populace, and they consume water at 140 liters per day per person. Rate of filtration is also given, and looks like we need 5% of the filtered water for storage to meet the backwash requirement, right. So, here I guess I should have been clearer. We let us say per day 5% of the water consumed per day we need it for backwash, and we are going to have to calculate the number of filter beds and one for standby, assuming that the ones that you are going to design will need maintenance from time to time. And what is the information that we have, where from the relevant aspects I can calculate the total surface area. So, they say that the surface area per bed is, or per filter is 40 meters square. So, accordingly we can calculate the number of filter beds. So, that is relatively straightforward. And what is the backwash velocity, and what is the head required to expand filter bed depth by an additional 0.66 meters, right. So, I want to know the backwash velocity and also the head required, in a sense the energy required to expand the filter bed depth by an additional of 0.66 meters. What is given? The porosity of the unexpanded, keep in mind that this is the unexpanded bed, right, and coefficient of drag, I guess kinematic, depth, this is the depth of the unexpanded bed and we want to expand it by 0.66 meters during backwash, the diameter, geometric mean and specific gravity. Yes. So, this is the information we have. Before we dig further, let us see, or let us look at the approach that we are going to take. So, first aspect is we have the population, right, population, and we know we have the relevant consumption per day 140 liters per person per day. From this I will be able to calculate the flow rate Q, let us say, right, and depending upon the need for backwash volume, let us say, and we talked about per day. So, we know we need to look at 5% additionally, let us say, yes, and I also have the overflow rate filtration here, rate of filtration. From that it is relatively straightforward, simple calculations here and there, and we will be able to come up with the area here for the filter beds, right. So, first let us get that done, okay. Again, or backwash velocity and also head loss required or head required. Head required for expanding the bed will be nothing but the head loss for that particular expanded filter bed depth, I guess, right. So, we have an equation where it is depend upon the relevant densities and such. This is relatively straightforward, but with respect to backwash velocity, how are we going to do that? For this, I think we have formulas that give us the relationship between porosity of the expanded bed to velocity of, I think, the backwash by the Stokes or the inverse of it raised to some what do we say, function of Reynolds number. It is not exactly this, but this is something like this if I am not wrong. And from this I guess you can calculate the backwash velocity. But what do we need for that? For that we need Reynolds number. For Reynolds number we have relevant info, and I think we have the kinematic viscosity and we have the diameter, and I think we should be able to get that done more or less. But for that again too, I guess we again also need to have the Stokes velocity, and this Stokes velocity we will have to calculate first. So, with that we can get the Stokes velocity which is needed here and also get the Reynolds number. But how do we get this porosity of the expanded bed though? What is the approach there? And I think for that the approach was that we looked at the volume of the media in the unexpanded bed, volume of media, let us see, and that will be equal to the volume of the media in the expanded bed, right. So, from that we have a relationship and we have this cancelling out the area, surface area. I think we have something like this, if I am not wrong, right. And D is the depth, I guess, yes, or I guess I made a simple or silly mistake here. So, yes, obviously it can't be 1 minus depth of the expanded bed. So, this is based on, again I cancelled out the surface area here and we are just looking at the volume of the media or the support, let us say, right. So, here I have the relevant porosity of the unexpanded bed. I already have the porosity, not porosity, the depth of the unexpanded bed. I also have the depth of the expanded bed. I think I know that it is 0.8 plus 0.66, let us say, right. So, from this I can get the porosity of the expanded bed. So, once I get this porosity of the expanded bed, I can plug it into this equation, right. And I calculated Reynolds number, I calculated this Stokes velocity of settling, and then I will be able to get the backwash velocity. So, with that I will be done. But in general here obvious assumptions are that we are assuming that the head loss will be equal to the head that is exactly required, but that will not be the case. In general you will require slightly higher head or energy, let us see. Again we have looked at the approach, let us go forth and finish this up. So, total demand, we have the per capita and the total population. So, I get the flow rate required, let us see, right. Backwash requirement is 5%. So, we are increasing it by 5%, let us see, right. So, let me see what we have here, okay, 5%, yes. So, 1167, 1225. In general, if there are any calculation errors, you can look at them. And rate of filtration is already given, and I have this what is it, flow rate, let us see, right, volume per time, and here I have the rate of filtration. So, Q by AS will give me the rate of filtration, and obviously I need this surface area. So, surface area required for total filtration, I guess, or the total surface area required will be 81.67 meter square, but I think they mentioned that, or the question mentions that it is per bed we are limited to 40 meter square, right. So, it will require 2 beds and 1 additional should be equal to a total of 3 beds. One is for the redundancy in case something breaks down, let us see, right. So, I guess my poor memory does serve me right this time. We have 40 meter square, and from that approximately it is 3 beds required, let us see, right. Now, let us move on to the other aspects. We were asked to calculate head loss and the backwash velocity. Let us see how to go about it. So, specific gravity is given, density of water. Specific gravity is more or less with the gravity or the density with respect to a reference. The reference is water. The density of water is given. So, the density of the relevant media or the solid particle can be calculated, let us say, right. Specific gravity gives us the reference, let us say, or the density with respect to a reference, which in this case is water. What is the head loss? I guess we already looked at this equation, at least in this course. As I mentioned earlier too, you do not need to mug up such equations. Mass balance, obviously you have to understand that and apply that, right. So, here we have all the relevant variables and we can just plug them in. Density of the particle, of water, porosity of the unexpanded bed, depth of the unexpanded bed, and density of the water. So, we plug that in. So, head loss is going to be 0.6 meters, I guess, yes. So, what else do we have? So, Stokes velocity, we have the relevant equation, and this is specific gravity, the diameter, coefficient of drag, and from that looks like you can calculate the relevant settling velocity, and Reynolds number. So, we have the diameter, kinematic viscosity or the viscosity, and the Stokes velocity, I guess, and from that you are able to calculate the Reynolds number, let us say, right. its Frockheimer's flow as expected. Yes. So, Frockheimer's flow, we calculated the Reynolds number, we calculated the Stokes velocity, and now we will use the equation, or now we have to calculate the porosity of the expanded bed before we can put that into this equation or similar equation to be able to calculate the backwash velocity. Let us see how we can calculate that porosity of the expanded bed. That we will look at by looking at the media, right. So, okay, this is the equation that we have, and for that I need this porosity of the expanded bed, but because I know that this is the case, yes, volume of the media of expanded and unexpanded is going to be the same. The total bed, right, earlier it was closely packed, right, and now during backwash it expanded, the total volume expanded, but the volume of the media itself, the media which I am highlighting here, is still the same, right. So, that is why it is 1 minus porosity, I guess. Yes. So, area cancel out, and you see that I can calculate the porosity of the expanded bed given the other variables, and porosity of the expanded bed is supposed to be 0.53. So, I plug this into the relevant equation, yes, and we get the backwash velocity to be 0.39 meters per second, yes, and I guess with that we are done with the major aspect. So, until now we have looked at filtration, right. Let us just quickly sum it up, as in with respect to our water treatment plant, drinking water treatment plant, what have we done? So, we looked at screens and such, that is fine, and then we looked at coagulation and flocculation, yes. Why? We wanted to destabilize the particles, and that we achieved by coagulation, adding a coagulant, and then we have flocculation, bringing the flocks together or aggregating the particles and thus forming flocks which are heavier, and then we had sedimentation, right, and then you will still have some suspended matter, and that you are going to remove by filtration, and this filtration you have to backwash from time to time, obviously, to clean the relevant bed or media. So, that is something we have done, but there is a different kind of filtration which we are going to refer to as surface filtration. This we refer to as depth filtration. So, what is the surface filtration about, and how is it that we are going to achieve it? So, here we are going to use membranes. Earlier we had media, and let us say, you know, these are the media we expect is to be spherical, that is the assumption. So, this is the space through which it will go through, right, and there is a way to calculate this, I mean based on this diameter, what is this opening going to be and such, right. We looked at the relevant applications with respect to depth filtration and such. Here we are talking about membrane, right. So, here we have either organic, inorganic materials that act as the relevant membrane or that make up the membrane, we will look at that. So, depending upon the raw water quality, you can directly have membrane filtration, let us say, right. But sometimes you will have to look at softening before membrane filtration, right, depending on the relevant quality of the water. Yes, again you are trying to increase the size. So, if you can remove it, you are going to have less load on your membrane filtration, life will be higher. If required, you know, you will add a coagulant and then allow for flocculation, bigger particles, and then membrane filtration. If the load is too high and you have considerably big particles, you are going to first have coagulation, flocculation, sedimentation, and then membrane filtration. In India, certainly this is what we need, but typically I do not think in India we have a lot of membrane filtration based full scale water treatment plants. Anyway, or one more thing is raw water. So, here it is post treatment, I guess, membrane filtration before it goes to RO or granular activated carbon. So, simple filtration, lime softening, direct filtration, and coagulation, sedimentation and such. Again, nothing to mug up, but just to understand. But when we are talking about membrane, what is it that is going to drive this particular system or the water, and what happens here? For example, in depth filtration we had media of sand and we had water at considerable head. That head is driving the relevant water through, and obviously you have head loss both due to the clean bed and also due to the ripening bed and such, and we looked at this aspect. So, here you are going to put in a driving force. What is the driving force? It can be physical, chemical or electrical, but here we are going to have pressure. The pressure is the driving force here, right. So, what do we have here? Just some terms to keep in mind. Feed, right, the feed water, which is the raw water that comes through or that comes in contact with this semi permeable membrane, and you have the particles typically based on size being rejected. You have going to have rejection, and the water that comes through, which we are going to use for our own purposes, is the permeate. So, feed and permeate, and this particular particle is rejected. So, the concentration in this particular reject or such will be relatively high. So, it can then be called concentrate, or as you can see, it is accumulated and the rejected material is migrating back into the solution. That is why we call it as concentrate, right. So, feed, permeate and concentrate, these are the things to keep in mind, and what is driving the system? It is the pressure. Let us move forth. So, here I have the feed, yes, and here is my membrane. Here the concentration is too high, something that I won't want, and after passing through the membrane I have the permeate, yes, and CP out, the concentration is lesser than this concentration of the feed. Okay, I should not have looked at this, but I should have mentioned concentration of the feed, and because the particles are being rejected here, or some of the particles, suspended particles are being rejected here, the concentration of the particles will increase, and that will come into the concentrate, or it is called retentate or rejectate. Let us see. So, if somebody asks for a mass balance, I will not look at internal aspects, I will apply the mass balance all around this, let us say, to be able to conduct the relevant analysis, right. That is something to keep in mind. So, again that is the representation. If I am looking at mass balance, this is what I can look at: feed, permeate and retentate, reject or concentrate. So, here we have some terms or some variables. So, rejection, let us say, percentage rejection, 1 minus Cp, I guess this should have been P, yes, Cp by Cf, right. Contaminant rejection, you know what is the rejection percentage, let us say, right. And what is the recovery? Q permeate by Q feed, Q permeate by Q feed. Why is this important? For example, in homes you would have seen your RO systems. Again, RO is not relevant right here, but it is similar, slightly similar anyway. It is also a kind of membrane, but based on osmosis or reverse osmosis. So, you would have seen that from your RO based system you would have a drain pipe to your relevant sink, while here you fill up your water, right. So, what is this? This is that reject or retentate which is high in concentration. So, for RO, this amount or the flow rate of the rejectate as a percentage of the feed is very high, right, or the recovery for RO is, if not very high, the recovery for RO is less. But in the case of the filtration, when we talk about filtration, we are talking about ultrafiltration and microfiltration, or I should have said micro first and then refer to ultrafiltration. Recovery is reasonable, around 95% or 90% and such. That is something to keep in mind. But again, you are going to have rejection, and then obviously we are going to talk about the recovery with respect to water, rejection and such with respect to the contaminant, right. So, these are some terms to keep in mind. So, what are some configurations of this microfiltration and ultrafiltration? Obviously, I need pressure or energy or pressure to pump the water through or to push the water through this particular membrane. So, I am going to can have water, what do we say, a pump, and pressure is created in this way, and here it is at the atmospheric pressure in general, or I can have feed water here and the membrane in relevant tank, and via vacuum or suction I am going to pump this out here, right. Pump suction pulls the water through the media, right. Pump suction pulls the water through the media. That is why you are again going to have a difference in pressure between here and here, let us say, right, transmembrane pressure. So, that is something to keep in mind, just some generic configurations. So, from Kittunen et al, we have some great figures of different membranes. So, let us look at what we have. So, first this is based on SEM, scanning electron microscope images of a 0.2 micron, keep that in mind, and look at the kind of membrane we have. It is polyether sulfone microfiltration membrane, right. So, that is something to keep in mind, right. And first one is cross section of the membrane. If I cut the membrane, you know, how does it look like? So, you see that there are pores, right, a lot of pores. So, obviously, for a suspended particle of size greater than or even equal to this particular pore size, you know, it is going to be pretty difficult to go through here, right. Again, you see the relevant pores or the relevant structure, and magnification of the membrane surface at the top or of this surface, right. This is the surface and we are looking at it here, right, this particular part, and this is obviously the cross section. Again, please note that this indicates the thickness 50 microns. So, you can understand the thickness that we are talking about. Yes. Okay, so let us move forward. So, here you can see the pore size and the particles are going to come here, particles meaning suspended particles in the water, and you have pores of different sizes, but again you understand how it is looking in the cross section, right. So, they are going to be removed by filtration. Here the primary mechanism is straining or screening, let us say, right. With respect to depth filtration, we looked at various aspects, sedimentation, flocculation, right, and such, but here it is usually only screening or straining. So, we looked at the cross section here in greater detail and the surface. So, again you are talking about exclusion based on the relevant size here, right. So, let us move on, and here we are looking at this particular membrane. Earlier we cut this and looked at it. So, these are again SEM images, I guess hollow membrane here, but let us look at that. SEM image of a hollow fiber membrane usually used for ultra microfiltration and ultrafiltration, right. And water permeating hollow membranes, as in what happens is you have different kinds. Water will go through here, right, go through the screen through this particular, what do we say, hollow portion here, and then the particle is going to be filtered out here and the water will permeate through, right. So, that is one way for it to go out through. So, the permeate will be here, the particles are going to be what do we say, removed or filtered at this particular surface. So, that is one way, and different one, I guess, ceramic tubular membrane, again different kinds of membranes, but I just wanted to show that. So, what is the phenomenon? As mentioned, this is the most usual one. You have you saw the pore sizes. So, particles bigger than the pore size, that will be strained out, but you also have particles that are relatively smaller than the pore sizes, and depending on the type of particle or type of material, for example, if it is NOM, let us say natural organic matter, that will be adsorbed on the surface of this particular particle, and this will be an issue because it will cause fouling of the membrane, right. Natural organic matter, that will lead to fouling of the membrane, leading to greater and greater pressures being required for the same flow that has to be achieved, let us say. And sometimes you will also have finer particles being trapped by cake, but again you will keep backwashing the membranes usually. So, that is one aspect, but again this is one possible mechanism, right. So, types of surface filtration. When we talk about surface filters, we have two categories here, micro and ultra filtration and nano and reverse osmosis. So, these we do not refer to as filtration, even though we have nano filtration there. When we talk about filtration, we are talking about micro and ultra filtration. Micro filtration typically suspended solids, and ultra filtration typically colloids and even some molecules, but most of the bacteria and even some viruses, some not all, can be removed by ultra filtration. We will look at this in greater detail. So, obviously, if the pore size is less, size is less, I will have to apply greater pressure for the water to go through, right. Obviously, that means the cost will also go up, right. That is one thing to keep in mind. So, conventional filtration, well, you see not much, but with respect to microfiltration, again keep in mind that it is one order of magnitude lesser here. So, microfiltration, yes, here, and ultrafiltration and nanofiltration considerable overlap. So, only thing is greater pressures, but again we are looking at smaller and smaller sizes. We are talking about different separation processes, right. So, here are some aspects we need to keep in mind. I will primarily look at micro and ultrafiltration here. Obviously, pressure is increasing, right. Why is that? Pore size is decreasing as we go from left to right. In general, the typical configuration is the hollow fiber, the picture for which we looked at earlier. Spiral wound is usually used for nanofiltration and reverse osmosis. Reverse osmosis, we will talk about this later, right. So, that is something to keep in mind. Water recovery, as we mentioned earlier, for microfiltration pretty good, for ultrafiltration, yes, reasonable, and even for nanofiltration, I guess, but for reverse osmosis you see that it is relatively less. That is something to keep in mind. Flux, right, volume of water going through per meter square of your surface area of the membrane per day. Here it is relatively less and getting lesser, right. And one aspect is, we will consider this or look at this later, if the flux is so less, then how am I going to achieve this level of what do we say, volume of water treatment within a reasonable plant area. We will come back to that, right. That might mean that I might need a huge plant area, right. Well, that is not the case, we will look at it later. So, what are the different kinds of particles that can be removed and such, we will look at that. But one aspect is, as the membrane pore size decreases, right, or let us say pore size here is highest, right. As the membrane pore size decreases, the pressure required will increase considerably, right, and then the money and such too, right. The cost for reverse osmosis are due to two factors. One is the pressure, and also because of changing the RO membrane from time to time. Microfiltration typically will remove bacteria and bigger particles, certainly suspended particles, most of the suspended particles in this range. And ultrafiltration will remove, I guess they are saying proteins, but in general even some viruses, not all will be removed, and any bacteria that is left will be removed by ultrafiltration certainly. So, these are the two aspects we are going to be concerned about, let us say, right. So, let us go forth. So, membrane configurations, there are two kinds of flows. One is the water is coming in like this, I am also applying the pressure in this way, and the permeate is going through here, right. So, only some goes through and a lot of particles are trapped here, and this is the membrane. The other one is the cross flow, right. So, flow is going through like this, and the superficial velocity that is coming towards this. So, flow is going through here, right, but pressure is being applied in the different direction here. So, this velocity will be around 10 times lesser than this velocity, and again you are going to have permeate coming through. Why is this relatively better? Because you do not want to have scaling or a cake being developed on the membrane. So, with this kind of cross flow, you will see that this cake formation is relatively minimized. You can think of it as built-in washing, but here you are going to have dead end flow. So, this cake formation will be greater. So, backwashing is required often, but for the kind of what do we say, hollow fiber ones that we use, typically at least I have seen or came to know that people look at dead end. Cross flow typically used in RO, at least you would have seen this in your homes, right. So, that is one aspect to keep in mind. And the reason is, or another aspect to consider is that for this, the what do we say, removal rate or such is such that you will have to recirculate this water quite a lot, and it can be as high as 25 or 30%, let us say, and that for a bigger plant will be a huge volume of water, this recirculation, let us say, with the water that is coming in. So, that is something to keep in mind. So, for membrane filters we looked at this micro and ultra filtration. This is the hollow fibers, this is the usual one, and we looked at this, right, water is going through into the plane, right, and spiral wound. So, water is going to flow like this and such, we looked at this, and then is going to be collected here for typically RO and such. This is what we are going to have, right. Let us move on. So, here we have the hollow, right, and spiral element. We will talk about this in the relevant RO relevant section, but here you can see the relevant flow. Feed flow is coming in, residue is coming out like this, and the permeate is going to go through the spiral process, and you are going to have this the permeate being collected in this perforated central pipelets, and you can see the membrane out here and the permeate spacer, right, membrane and the permeate spacer. Again we will talk about this in the relevant section for RO. Here you see the relevant figure again for spiral, I guess, right, but again this is for a bigger system. So, filtration cycle, you will have to have backwash to dislodge the particles from time to time, similar to your depth filtration, and sometimes you will add agents, chemical agents, depending upon the type of what do we say, scaling or such that is occurring on your membrane. So, one aspect is we should consider the filtration rate, as I mentioned, between membrane filtration and rapid granular filtration. Here you see that it is 5 to 15 meters per hour or 5 to 15 meter cube per hour per meter square of the relevant bed, but here you see that it is pretty low, what, 10 times or 100 times lower. So, how is it that I am able to achieve the level of treatment required while also being able to cater to the needs of the this high, what do we say, volume of water? As in, I can't have a huge plant, The reason is that you can, what do we say, pack it well enough, the surface area of your particular what do we say, packed hollow membranes is going to be relatively high. So, per unit volume there will be more surface area. So, that is the relevant aspect here, that is how you are able to achieve feasibility. And pressure obviously you see relatively higher and I guess comparable, but relatively lower for rapid granular filtration. And filtration cycle, we know that it is 1 to 4 days here, you see the order, it is relatively less, let us say, right. And ripening period is none, here we know it takes around 2 hours for that ripening to occur, so that you have the peak efficiency of filtration, right. So, let us, so as I mentioned, straining is the major aspect, here it is depth filtration. Let us move on. So, membrane fouling will occur from time to time, right. So, here is the hydraulically irreversible fouling initially. So, when fouling reaches this particular aspect or high enough, your transmembrane pressure required to pump that particular flux through, all right, will be higher. That is what is happening with time. The pressure required to pump that particular water through is increasing. So, at that point you are going to stop and backwash, and then the pressure required is going to come down and you are going to have these cycles. But slowly but surely you see that your starting point you are losing that, right. So, even though you backwash, you are never able to come back to this particular or more or less near that particular initial case, and then you are going to sometimes have the backwash with chemical cleaning and you will come back to a relatively better scenario, but still you will have some fouling, and this is irreversible fouling now, right. And over time obviously different, I mean over few months or such, this membrane is going to be irreversibly fouled and you will have to apply way too much pressure to get your water through. That is something to keep in mind. And one other aspect is, we talked about the issues with respect to natural organic matter. It will interfere with activated carbon, with chlorine it will form disinfection byproducts. Here also it is going to cause an issue as in membrane fouling, let us see, right. It is going to foul the membrane pretty quickly. Yes, that is something to keep in mind. So, design, what is it that I am concerned with? So, this is the flux. Flux is the volume of water per meter square surface area of my membrane per hour, right. It is going to be depend upon the transmembrane pressure, the difference in pressure, how much am I going to apply, right, and also this membrane resistance that varies from one particular system to the other. So, membrane area from typical flux, right, flux and transmembrane pressure we just looked at that, cleaning by backwash and sometimes obviously chemical cleaning. So, with that I will end this session, and in the next session we will talk about disinfection and disinfection byproducts, but because we discussed that in wastewater treatment, we will be very brief before we wrap up the water treatment related aspects and move on to looking at processes that are now coming into greater vogue, as in adsorption ion exchange, right, reverse osmosis, advanced oxidation process, right. But that is enough for today, and thank you.